Hi class, good morning. Um, we are going to continue with our lectures on electrodynamics, and um, again, we're using as our reference Introduction to Electrodynamics by David J. Griffiths. Please buy this book when you have extra resources. Anyway, I'd like to make a roll call for now. We have Danica De Lima, um, Nelba Grace Lapining, Marsden Badlisan. Uh, Unfortunately, Hasni Aminuddin doesn't have internet connection today, so he can just replay this lecture. We have Rena May Tondo. We have Arya Nicole Halibas, Jesril Daigam, David Paul Hinayon, Michael John Gomez Galliera. We have Joven Steve Adaptar. By the way, what took me so long, I didn't have a stable connection this morning. So I was waiting, but it came like 9:49, yeah, something like that. And Jay Dulog, Laika Jen Laure, Eugene Diaz, Era Bilieno, Liza May Rodriguez, and some more are still coming. Sorry for that, class. This is a new normal. We don't have control over um, these things. So today we'll be uh, going briefly, swiftly with going back to the direct delta function. So the direct delta function has a plot that looks like this. It looks like um, a spike at x equals 0. So at x equals 0, the value of the direct delta function is infinity, and at x not equal to 0, it's 0. And the integral, it's a property of this direct delta function. The integral of the direct delta is it's integral from negative infinity to infinity is equal to 1. So by the way, the limit here should include the argument of the function such that the argument is equal to 0. So you can say that this is from negative 2 to 2 because x equals 0 is between or is included in 2 to 2, negative 2 to 2, and still you have the integral equal to 1. Or this is from negative negative 0.5 to 100. This is still equal to 1 because the argument here, in which the whole thing in the argument is equal to 0, is included in the limit. So in this case, the argument that makes this x equal to 0 is x is equal to 0. So it's between or within the limit of the integral. So it's equal to 1. So you can change the limit here. Although formally this is negative infinity to positive infinity, but for as long as the limits of the integral includes the value which the whole argument here is 0, gives you an integral of 1. So again, delta x is not technically not a function, but it's called a distribution or a generalized function distribution. So anyway, you can also um, associate Dirac delta as the limit of a function such that are such as rectangles Rx, Rn of x with height n and with width 1 over n. So as the height increases, the width decreases. So it's the limit as n goes to infinity. Or an isosceles triangle Tn of x with height n and base n 2 over n, as you can see here. So as the height increases, the width decreases. So here you have longer height, and then you have a narrower width. In this case, also for the triangle, you have longer height, and then you have narrower base. So one property of the Dirac delta function is that when you multiply it with another function, when you multiply this with another function, f of x, say, you this is always equal to f of 0 delta x, because the delta x here is 0 everywhere except at some point, and in this case x is equal to 0. So this can be rewritten into f of 0 because only at x equal to 0 has this delta function have a value. So these are equal. And of course, when you integrate this, expression, if you integrate the left side, you should also integrate with the right side with respect to the same variable. So in this case, you integrate f of x delta x with respect to dx. This is just equal to f sub o. F sub o is constant because you have already substituted x with 0, so you have to put f of 0 outside the integral, and then you will be left with this, and this is just equal to what? This is just equal to 1, according to the definition of the Dirac delta function. So this is f of x equal to 0. We also have, by the way, we have John Kester also on the roll here. Now, we can shift. Actually, the spike of the Dirac delta function can be shifted, like here, for example. It's not now at 0. It's now at x equal to a. So the Dirac delta function can now be redefined with this. So it's equal to 0 at x not equal to a, but it's at infinity if x is equal to a. So in this case, the Dirac delta integral becomes this one. So for as long as the limit includes that value at which the argument here is equal to 0, the integral would be 1. In this case, a is the value at which the delta function has a value of infinity, so the integral here is equal to 1. In this case, a is between negative infinity to infinity. So that's it. So here's the graph. It's shifted. And of course, this is also true. That is also true. F of x is equal to integral of x minus a. F of a times, f of x times the Dirac delta function of x of x minus a is just equal to f of a, Dirac delta function of x. minus a. And again, from if you integrate both sides, the left side, if you integrate this and integrate this also with respect to dx, with respect to dx, so you will have also this. And now, as an example, we had last time integral of x cubed times direct delta of x minus 2 dx. Here in this case, you have what makes the 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 value of the argument equal to 0 in this case. Um, it's x is equal to 2. If x is 2, then the whole argument here is 0. So is 2 included in the limit? The 2 is included in the limit because it's from 0 to 3. So the 2 is between or within 0 to 3. So our integral would be 2 to the cube. So this one is the answer of that integral. And also, we had this what do we say, this expression before we last meeting. So if you have this as true, if this is true, if that expression is true, then look at this. We cannot cancel, but by looking at this, we can ignore this, we can ignore this, we can ignore this. We can also ignore this one, we can also ignore that one. And so what's left is D1 and D2. We cannot cancel that. We cannot cancel the things here. But we can say that D1, we can say that D1 and DX2 are equal. We can say that. We cannot cancel them. Okay, please, because this is like an operator, and this is not ordinary algebra that you're just multiplying to the functions. You are operating on a function, so it's not not easy just to cancel that. But you have to operate first, and then you see the result at the end, and then that's when you can cancel. But in this case, just looking at it, if they look, some of the terms are look the same, and then when you actually have the value of fx and dx1 and dx2, then you can say that they're equal. So anyway, I'd like to welcome John Oliver Abian and Grace Dave Torresino. Thanks for attending the lecture. So as an example of that, we show that this is equal to, we show that this one is equal to this one. So like, for example, in particular, you have delta x, katulge kung mata. For example, you have this Dirac delta of negative x. This is just equal to 1 over negative 1, but 1 over the absolute value of negative 1, which is just equal to 1, the whole thing. And then you have Dirac delta of x. So let's show this. So we put a test function here, f of x, and do the integration of this. We do the integration of that. By changing variables, the last time we did, by changing variables to y equals kx, then we have x is equal to y over kx, so that your derivative with respect to x, you have derivative of x is just equal to 1 over k times the derivative of y. so that you can change everything here. This one will be changed to uh, um, uh, to this, to a variable y, so that your fyk, what is the value of y that makes this 0? Y is equal to 0. So this is y 0 over k would just be equal to 0. So you take that out of the integral f of 0 and 1 over k. But what is f of 0? F of 0 is this one. F of 0 is this one. So that you will have this one as equal to, uh, you can put back back the 1 over k back to the integral in this case. So with d1 equal to d2, this one, so you can say that um, delta kx and this one are both equal. So that's what we had last time, and then we continue with we continue uh, with the lecture here. So we generalize the Dirac delta function into 3 dimension, um, and so the Dirac delta function can be uh, given by this product. The Dirac delta function in 3 dimension. In this case, it is now a function of a vector r, where r is of course where r is equal to x, x hat plus y hat, and z hat, and this is just equal to this is just equal to the product of the 3 Dirac delta functions. So um, all of these Dirac delta function behaves the same, but the arguments are of course different. We have a different argument here, here, and of course here. So that includes the 3 dimensions of the Cartesian coordinate system. So here, um, if you integrate this, so this is just a triple integral with respect to x, y, and z, and the integral would just be equal to 1. And you have this still is a default, um, the same thing that that was done in the 1 dimension, except that the arguments here are all vectors. So it's still the same. So now let's go to this function. We go back to this function r hat over r square. So what is this? This is like um, the distance displacement function. So the divergence of this function is equal to 4 pi uh, the Dirac delta of r, because when we solved this before, if we go back here, we solved this in we solved this here. The integral of this with respect to dr is equal to is equal, this, the integral of this is equal to the integral of b dot dA by Gauss law, by Gauss integration law, and we got 4 pi. We we argue that this is wrong. The zero here is wrong because precisely because you're integrating a function where you have an r square, you have an r square as the denominator here, and actually the limit here is from the limit is from 0 to infinity, and if you include 0 here, that will make this this thing, it makes infinity, and so it cannot be integrated. So that's why this answer is wrong. And in this case, we did this according to Gauss law. The integral of the divergence is just equal to the integral with respect to the integral of the divergence of v is just equal to the uh, equal to the integral of v with respect to an area, with respect to a closed surface, I mean. And we found that this is equal to 4 pi. So therefore, this one is equal to 4 pi. This one is equal to, this one is equal to 4 pi times a Dirac delta function. So that's why that's why it's written here. So your v is equal to r hat over r squared. So in electrostatics, electrodynamics problems, we generally use r, the separation vector, this one. And we know the definition of this. R is just equal to field point minus source point. So this is field point minus source point. So most of the time we do that, and this is just the equivalent of the divergence of that function, vector function. So in this case, what's inside the argument is r minus r prime. This one is r minus r prime here. And in this case, the differentiation is with respect to r. The differentiation is with respect to r. So your r prime is held constant. So remember that. But anyway, you will be able to check that when we solve problems. So now this is this one, this function, vector function, is incidentally equal to the gradient of 1 over r. This is gradient of 1 over r. So in this case, you can work, this is more convenient to work with. Why? Because this function does not have what's inside here is does not have does not have direction. The direction is given by the del here. So in this case, it's more convenient to work on that. And then if you multiply, if you take the gradient here, take another gradient here, take another gradient of this, and take the gradient of this, so it will just look like this one. And this double gradient, I mean the divergence of a gradient is just equal to this one. And then of course this one, the whole thing here is equal to this one, equal to this one. And so you have that here. Only that this is negative because of the definition here. So um, you have now this expression. So you should remember that. Okay. So now let's go to an example. So this one is J. Actually, J here will be just current density. Later on, you will know that J is a current density. So the integral of J, we're looking for the integral of J, this one. But this one you can write as a Dirac delta. So that it's easier to integrate this time. So the J, r squared plus 2 would just be that, and then this one would just be 4 pi delta Dirac delta. So you're integrating that with respect to a volume V. So you can what makes this equal to 0? This is when r is equal to 0. So what is the magnitude of r equal to 0? The magnitude of r equal to 0 is also 0. So that, by the way, this r is a vector and this r is the magnitude of the r. So if this is a 0 vector, the magnitude of a 0 vector is also 0. So that you will have a 4 pi. The 4 pi here you can take out of the integral. So you'll just be integrating. This is supposed to be 0 square. No? This is, you have a square here. 0 square, anyway, that's still 0. Plus 2 is equal to 8 pi. So this is equal to um, this is equal to 8 pi here. Now let's look at integrating it the long way. Here you have this integral again, and then you by integration by parts, that can be transformed into this integral. Integration by parts is in equation 159. So let's look at that. One 1.59. I mean. So okay, this one here. So you can rewrite the equation as of this as this form, as this expression. So you can compare. You can compare the quantities here, and then you can write them like this. So anyway, let's look at this. So let's now look at this one. Mhm. So your r square, r hat over r square times that with the gradient of r square plus 2, you integrate that with respect to a volume. And the second term is your r square plus 2 times r hat over r square is dotted to the volume dA. So the gradient of r squared plus 2 is just equal to 2r r hat. You can um, calculate that. You can calculate that by longhand, and you will find out that this is just equal to that. And of course, there's also a formula because this is a generalized derivative. The derivative of like dx derivative of x to the n is just equal to n minus 1 times x. Oh, derivative of x to the n is just equal to n times x to the n minus 1 over yeah, n times x to the n minus 1. So in this case, you're getting the derivative of r squared. So this is just 2r r hat. That is the it will have direction r hat. Then the derivative of 2. This is the generalized derivative. The derivative of 2, this 2 is a constant, so the derivative of, or the gradient of 2 is just 0. So you will have this. And so uh, r hat, um, you have this one, um, you have this one as this, as that. So um, you dot r hat and r hat, that gives you 1. R hat is equal to 1 because they are unit vectors. So this will just be equal to 2 over r integrated from integrated by the whole volume d tau. So this d tau is equal to r squared sine theta squared dr d theta d phi. And the integral with respect to phi is 0 to 2 pi, which gives you 2 pi. And then the d theta and sine theta, when you integrate that from 0 to pi, that will just give you 2. So everything will just give you an integral of r dr from 0 to r. This is the volume of the sphere. So you have 8 pi here outside, and then you just integrate with from integrate this expression from 0 to r, and this will give you 4 pi r square. The integral of r dr will just be r square over 2. From 0 to r will just give you r square over 2. So the other integral that we have to solve is this one. And for this case, you'll have dA that is equivalent to this in the spherical coordinates. Why is this the dA? So we are looking at the direction of dA that is parallel to r hat, and the dA that is parallel to r hat is also the dA that has the direction r hat. So that when you dot r hat and r hat here, um, it will give you 1, because if you dot with theta hat, uh, r hat time dot with theta hat will just give you 0, and r hat dot phi hat will also give you 0. So it does not give you anything. So the only area that could be dotted to r hat is the differential area with direction r hat to give you a meaningful result. So in this case, the area is r square. If you look at the spherical coordinates, the area would just be equal to this. And you substitute it here. You substitute this one to here. And then if you substitute that, you will have uh, this. Um, you set now r, the radius as equal to the capital R, this one. You set this to capital R here, so that you can cancel them. Anyway, you are integrating, the boundary of the sphere that you're integrating is r is equal to r. So now you're left with the variable theta and d phi. So the integral of d phi is from 0 to 2 pi, so will give you that will give you 2 pi, and then the integral of sine theta d theta from 0 to pi will give you 2. So that 2 times 2 pi is equal to 4 pi. And then you have this as a constant. So you will just have this expression as the integral. So you now have two expressions. This one you have integrated to be you have integrated that to be, this one is integrated to be to 4 pi r square. That's negative 4 pi r square. Negative 4 pi r square if you consider the negative here. And this one has an integral equal to this. Sorry. Equal to this. Sorry. Equal to that. So that if you subtract this one from here, this one is equal to that. So if you subtract this to here, or from here, I mean, if you subtract this one from here, it will just give you this answer, which is what we expect, 8 pi. So you can do the long way and you can do the short way using Dirac delta function, and you still get 8 pi, same as here. Yeah, the same as here. You still get 8 pi. So all you have to do is know the techniques of integration, and that will just make your problem easier to solve. So this is now the last part of the chapter 1. So in chapter 2, we will begin next week, and then we will also on the weekend I will try to solve some problems, and I will post it in our forum. So I hope you've studied the problems, the sample problems that I have posted. For now, I will not give you some problem sets. Maybe towards the end of October, I will give you some problem sets. But for now, let's do away with problem sets, because um, um, I know that you're also busy with your other subjects, and then I just would like you to understand the lecture first. Then we will do some problem sets, simple problem sets. So anyway, this the last part would be Helmholtz theorem. So there are two theorems for uh, Helmholtz, the curl for the curl and for the divergence. So anyway, um, all of electrodynamics are electric fields and magnetic fields. The study of electric fields and magnetic fields and how they interact, how they're combined. So um, and these electric fields are fields, they come from a source point, and as an electric field, it diverges from a source point. So for example, if you have a positive charge, the electric field goes out of the charge um, radially outward. But if you have a negative charge, the fields are going to the charge by convention, radially also. The magnetic fields, on the other hand, is another field. This is synonymous to electric field, but on the other hand, magnetic field is produced by moving charges, as we will know in the succeeding lectures. Magnetic fields are produced by moving charges. So if the charge is moving this way, there is a magnetic field that curls the charge. It curls the charge in this direction. So if it's moving that way, the magnetic field that curls the charge is in this direction, if that's moving that way. So the fields are always expressed in electric field and magnetic field. So by the way, they are um, denoted by E and D here. So again, the fields are vectors. And of course, if they are vectors, then uh, their derivatives are done by the del. So the derivatives are done by the del. This one here. So for a vector, you have the del of f, the curl of f, because these are vector. But if this is ordinary numbers, if f are just ordinary numbers, then the del here would just be d over dx, something like that, or d over dz, or d over dy. Um, Now, suppose that the divergence of f, this one here, the divergence of f, the f here could stand as an electric field or a magnetic field. Um, Suppose the divergence of f is a specified scalar function d. So you have this. And the curl of f is a specified vector function c. This is supposed to be in boldface. So this one here. Uh, of course, the divergence of a curl is always zero. So c is always zero. Um, can the function f be determined? The answer for that is not quite. It lacks something. What's lacking there is some specification called boundary condition. You cannot still determine f here because, like, for instance, there are many functions whose divergence and curl are both zero. And examples of that is like your f is equal to zero. The divergence of this is zero. This is a trivial function. This one, this function also gives you zero. I mean, the divergence and curl will also be zero. For this function also, the curl and the divergence are also zero. So it's not it's not a guarantee that you can find the vector function f by having this specification. You need another specification called boundary conditions. And what is that boundary condition? The boundary conditions actually will be more elaborated in chapter 3. And this is just an introduction on the mathematical aspect this course. So we will elaborate more on the boundary condition in the succeeding chapters. Maybe we'll reach that chapter in November. So anyway, but these are the first theorem for Helmholtz. So if the curl of a vector field f vanishes everywhere, this one, then f can be written as a gradient of a potential scalar, a scalar potential. I mean, this is a scalar potential. This has no direction. The direction will be given by del, so that your f will be a vector. So, by the way, the minus sign is the minus sign there is just equal to I mean, the minus sign is just a convention. You can also use positive sign here. By the way, if you recall, the force is the force, which is a derivative of the potential energy in classical mechanics, or in mechanics. You encounter this as the force is equal to the derivative of the potential u with respect to some distance, or y or x. So that's just the same for electrical scenario, but in this case you are dealing with three-dimensional derivative. So for theorem 1, if your curl of f is equal to 0 everywhere, then it must satisfy b, c, and d. So the integral from a to b of f dot dl is independent of the path for any given endpoint. So whatever endpoints you have, only use those endpoints, because the paths will not matter in the integration. So you have the fundamental theorem of calculus to solve this. We discussed that in previous lecture. The closed integral of f dot dl is equal to 0. So they must satisfy all these conditions here. F is, of course, a gradient of some scalar here, as written. So this is the first of the Helmholtz theorem. So this one. The next one is for the scalar potential, divergence of a vector field. This one. By the way, there's a note here. The scalar potential V is not unique. This is not unique. That is not unique, because any constant can be added to V. Any constant can be added to this potential, but it will not affect its gradient, because the gradient of a constant is always 0. So you can add this. You could put plus 7 here inside V, and the gradient of 7 will just be 0. So it's not unique. With the divergence, with the divergence of a vector field, the theorem also satisfies these conditions. This is Helmholtz theorem for the divergence of a vector field F. So if the divergence um, vector field F vanishes everywhere, this one, if it's 0, then um, F can be written into curl of a vector function, say A. So um, the following conditions are equivalent. So um, you have to uh, remember these conditions for vector function or vector potential. We call this vector potential. Vector potential A. So as a vector potential, it has direction. It has direction r hat, theta hat, and phi hat, or r hat, theta hat, and z hat, or x hat, y hat, z hat. So you have if the coordinate system is specified, you have to use those unit vectors. So anyway, for the divergence of a vector function, if this is 0, then um, if this is satisfied, then all three is satisfied. So if the divergence of f is 0, then the integral of f dot dA is independent of the surface. So any surface, whether it's a cubical surface or a balloon surface, um, or but of course you have to be careful of this statement for any given boundary line. So if your boundary line is a rectangle, whatever surface uh, is enclosed in that boundary line, whether the surface going here is a ballooning on this direction or in ballooning on the other side, the surface does not matter. It's or you can choose a flat. It's much easier if you choose a flat surface, because the dA there would just be regular dA, because if you choose a curved surface, the dA would be different in different parts of the surface. The dA would have a different direction. So uh, but no matter what surface you use, it doesn't matter. It gives you the same answer. So the closed integral also of f with respect to dA will give you 0. And f is the curl of some vector, um, which is the vector potential. So again, the vector potential is not unique, because you can add any scalar function to A, or you can add the gradient of any scalar function to A without affecting the curl. So you can add to A uh, gradient of phi, for example. So if you take the curl of A plus the curl of that gradient phi, for example, it will just give you 0. The curl of the gradient is always 0. So incidentally, we can write f um, to be the sum of these two. We can write, in general, we can write f to be the sum of the gradient of v and the curl of a vector potential. So that's for the Helmholtz theorem. That this is the last topic of chapter 1. So what I would like to do now is, on the weekend, is I will solve some sample problems and post it to our forum in um, uh, Google um, Google Classroom, and also in the Mole Classroom. And then maybe starting next week, we will have an interaction session, and that would be done in Google Meet or in um, Zoom. So I think with that you have to download. I don't know if you would have to download Google Meet, but I'm sure that the Zoom you have to download also. So I will just put the link on our Mole environment and in our Google Classroom for that. So for now, that's our lecture. It's kind of short, but I hope you've learned something. Thank you. I hope in the next lecture more of you can join. Um, good morning, sir. There are some Jan Kester is here, and also Grace Dave Torsino. Next week na jud po, next week na jud po, sir. If SQ la, what is yes? If sa laptop, sir, naara ang Google Meet sa Gmail. Ah, okay. I don't know about it, but you can experiment. Check if your phone can have a Google Meet. I think it works both in the uh, I think it works both on the laptop and on the cell phone. Okay, no problem. No problem. So that's all for now. See you next week. See you next meeting.